The temperature is -2 degrees Celsius. If the temperature rises by 15 degrees Celsius, what is the new temperature? So I would recommend using a vertical number line to visualize the situation. All right, so we're starting at -2 degrees, and then the temperature rises 15 degrees. So on the number line, there's your start at -2. And if we're rising 15 degrees, if we go up by 2, you have to go up an extra 13 degrees to rise up by 15 degrees. And when we say rise, we mean we're going back up. So the total increase was 15, but from 0, it was just an extra 13. So right there, it ends up being positive 13 degrees. In equation form, you have -2 plus 15, and that's equal to 13 degrees Celsius. Part B, at midnight, the temperature is -6 degrees. At midday, the temperature is 9 degrees. We're talking Celsius. By how much did the temperature rise? So I would recommend we can use the same number line. All right, so starting out, they're saying the temperature is -6 degrees Celsius. So we're right there. All right, and there, as you can see on the number line. And at midday, the temperature is 9 degrees Celsius. So this is where we end up, 9 degrees. And they want to know how much did we have to rise up by. So what you're going to do is you're going to add the 6 degrees to get back to 0, plus the extra 9 degrees to get from 0 to 9, and your total increase was 6 plus 9, which is a 15-degree increase. Another way you could write that equation is -6 plus the unknown is equal to 9 degrees, and then you would solve it by adding the 6 plus 9. But in the end, our final answer is that there was a 15-degree temperature rise. All right, draw a diagram to represent each of these situations, then write an addition expression that represents the final temperature. All right, so we need two things, an expression and a diagram. All right, so for part A, the temperature was 80 degrees Fahrenheit, and then it fell 20 degrees. Since those are some big numbers, we could go by ones, but that would take forever. Even going by 2s and going by 5s would take forever. So I would recommend at least go by 10s. I'm going to go by 20s because 20 is going to hit both those numbers nicely. And I started making the negatives, but I realized this is all going to be in the positive zone. So let's just do the positives. So if we start out at 80 degrees Fahrenheit, the temperature falls, that means it's going back the other direction, and we land on our final temperature of 60 degrees. Now we need an expression. 80 plus -20, because it's a falling temperature, and that leaves us with 60 degrees. So this is our expression for diagram A. All right, the temperature was -13 degrees Fahrenheit, and it rose 9 degrees Fahrenheit. And since these are smaller numbers, I could go by 1s, or I could even go by 2s. These are odd numbers, so you know what? I'm going to go by 2s. It's less writing, and we can just put it in the middle. All right, now you could go by 1s if you want to. You could even go by 5s, but if you go by 5s, you're going to have to estimate a little bit more. I also started going in the positive side, but then I realized if I'm at -13 degrees and the temperature rises 9 degrees, it's going to rise, I could count 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to end up back at 4 degrees. So my final temperature is 4 degrees, and my expression would be -13 plus 9. Since it's rising, that's a positive number, and that leaves me with -4 degrees. Notice that when the negative number is larger, like the magnitude of that vector right there is larger in the negative direction, then we end up still having a negative answer. Just a friendly reminder, the instructions ask us to draw a diagram and then write an addition expression. All right, last one. The temperature was -5 degrees Fahrenheit, and then it fell 8 degrees Fahrenheit. All right, for this one, we could go by 2s. I'll go by 1s this time. All right, so last one. If the temperature was -5 degrees and then it fell 8 degrees, that means that we're at -5. Falling 8 degrees means we're going to go 8 more. That's 5, 6, 7, 8. And you're going to end up at -13 degrees. So -5 plus a -8. Falling means negative numbers. And you end up with a negative final result. By the way, when both numbers are the same sign, the vectors point in the same direction, as you can see. All right. All right, complete each statement with a number that makes each statement true. Just a couple of reminders here. All right, so when the arrow points to the left, that is less than, and when the arrow points to the right, that's greater than. So it says complete each statement with a number that makes the statement true. So you might have chosen a different number than I'm going to show you. But with that said, guys, let's come up with some examples here. A number that's less than 7 could be positive, like a number like 5. It could also be a number like -5. So either of those would work. Anything that is to the left of 7 on the number line. A number that is less than -3 could be a number like -4. Anything that is left of the -3 on the number line would be less than 7. Or sorry, less than -3. All right, now this statement right here, part C, they're talking a number that is in between -0.8 and between -0.1. So if you're counting by, imagine these are like dimes. So that'd be like 10 cents, 20 cents, 30 cents, 40 cents, and so on. In the negatives, imagine you owe somebody like change or something like that. So what's in between -0.1 and -0.8? It could be 0.2, it could be -0.3, -0.4, -0.5, -0.6, -0.7. I'm going to say -0.3. And now we need a number that's greater than -2, meaning it's to the right of -2. So it could be -1, it could be it could be 0, it could be 1, to any positive number, 2, 3, 4, 5, etc., and so on, would be greater than -2 degrees Celsius. All right, decide whether each table could represent a proportional relationship. If the relationship could be proportional, what would be the constant of proportionality? So just a little reminder, the constant of proportionality is the number that is multiplying every single number in the table. So in a proportional relationship, they will all have the same number that they're being multiplied by. If it's not proportional, then there's not going to be a single number that works for all the numbers. All right, so looking at table A, the number of wheels on a group of buses. So let's say we have 5 buses to get to 30. That would be 5 times 6 is equal to 30. So if 8 times 6 is 48, then we might have a proportional relationship. It turns out that that is. 10 times 6 is equal to 60, so that works. And then 15 times 6, might need to check that 20 by 20 multiplication chart in the back of your notebooks, but that's also equal to 90. So my constant of proportionality is going to be the wheels per bus, and it turns out that it is 6. Each time it is 6. Okay, let's take a look at this real quick. Since they all are multiplying by the same thing, table A is representing a proportional relationship. All right, now let's take a look at table B. I wonder, is there a single number that we can multiply each of the number of train cars by in order to get the number of wheels? All right, let's try it. Now, if I'm being honest with you, trying to figure out what to multiply 20 times to get 184 is a little bit tricky, so I'm going to use division. 184, this is working backwards, divided by 20, and that's going to equal, all right, let's rewrite it like this. 184 divided by 20. 20 can go into 184 9 times. That's going to give me 9 times 20 is 180, with the remainder of 4, so that'd be 9 and 4/20. Okay? So that's the wheels per train car, 9 and 4/20. 20ths. Kind of interesting having 4/20ths of a wheel. All right, does that match the next one when there's 30 train cars? All right, 30 can go into 264. I'm going to think of it as 3 going into 26. It can go in there 8 times. That's 240. And before I even subtract, that's already different. 8 compared to 9. So this would not be proportional. Wouldn't be proportional, but let's continue because we do need to find the wheels per train. You subtract right there, you're going to get 24. And so you have 8 and 24/30ths. So I would basically just continue to use the same process of dividing the wheels by the number of train cars, and here's what the rest of them would be. All right, and notice that the numerator stays the same on, when there's 30 and 40 and 50 train cars, but the denominator changes, so it's not the same.